we know that today we are faced with many crucial societal challenges. We care about security, both in the physical world and in the cyber world. We care about environmental sustainability. For example, we rely on rangers to fight against poaching in the front line to stop the population drop of key species like tigers. And poachers would set snares to capture the wildlife, and rangers can patrol in the protected area to remove those snares, but the ranger resources is usually very limited. And we also want to reduce hunger and improve transportation efficiency with the help of crowd-based platforms. But there is still a huge room for improvement in the operation of all these platforms. And if we look closer into these problems, and there are similar problems, they all involve multiple self-interested agents, like the defenders versus attackers in the security domains, or the rangers versus poachers, or the crowd-based platform and its users. And the question that we want to help answer is how to allocate the limited resources and how to coordinate and communicate with the agents to achieve higher efficiency. More specifically, we have been working on developing game theory and machine learning techniques that can help tackle these challenges. In my earlier work, we had some successful attempts. We helped the US Coast Guard to design patrol routes to protect the Staten Island Ferry from potential attacks. Since there are many ferries running and there are only 2 patrol boats, the Coast Guard has to use used to choose one ferry and then ask the patrol boats to follow the ferry all along the way. And we modeled this problem as a defender-attacker game and designed a randomized patrol strategy for the defender. And this strategy asks the patroller to take a route sampled from a probability distribution, which is carefully calculated through linear programming with the goal of minimizing the attacker's maximum possible expected utility. And on randomly chosen utility functions, we showed that the potential risk measured by the maximum attacker's expected utility is cut down by half when using our game theoretic algorithm. And as our work is brought to the real world in April 2013, it has resulted in a radical shift in the patrolling tactics of the US Coast Guard. And as shown in this video, the patrol boat is actually making a U-turn, which would never happen in their previous patrols. And the US Coast Guard called this change in the patrol strategy a radical shift from point defense to zone defense, which is an analogy from the basketball game, because before they were defending against potential attacks to one ferry, and now they are defending against the potential attacks to high-risk zones. And they think our solution has improved the randomness of the patrols. And the professional mariners also mentioned that there was an apparent increase in the Coast Guard patrols using the new patrol schedules, while in fact the number of patrol boats and the patrol hours didn't really change. And our work, together with the optimization for protecting other parts of the port, is estimated to lead to a $33 million saving in 10 years for the US Coast Guard to achieve the same security level. And it continues to impact the Coast Guard patrol policy even now. So we, inspired by these successful attempts in my early research, we continue to see how AI can be used to tackle different societal challenges. And in the rest of today's talk, I will mainly focus on 2 parts. One is how to use AI for protecting wildlife, and the other is for reducing hunger. So in fact, when we introduce our work on this ferry protection to different audiences, we learned from people at the World Bank and several conservation practitioners that similar challenges exist in anti-poaching. So we started to think about how to better protect wildlife using AI. For example, in Uganda, lives of wildlife are threatened by the traps and snares, and conservation agencies send rangers to patrol. However, the cost of a snare can be as low as only $2, and the ranger density can be as low as 1 ranger per more than 100 square kilometers. So poaching remains to be a huge threat, and how to make the most out of the ranger patrol is a big challenge. Our first thought is to directly apply our game model and the algorithm for protecting the ferry to design the patrol routes here. But soon we realized that these problems are very different. Because here, in this problem, the attackers per se, who are actually the poachers, indeed launch frequent attacks because they place snares. They go to the protected area and place snares very frequently. And that also means that for us, it is possible for us to learn from the historical data, if any, to understand their behavior. And on the other hand, because of this frequent attacks, it is impossible. It is not so reasonable to assume that these poachers are perfectly rational and is going to maximize their expect utility and so on and so forth. So this inspires us to like come up with new ways to tackle the problem. So we first worked with Uganda Wildlife Authority and Wildlife Conservation Society, who have data, 12 years of poaching data collected during the patrols for the Queen Elizabeth National Park in Uganda. What we want to do is that we want to develop some algorithms that can convert these data to a prediction of the probability of poaching throughout the protected area. But we noticed that there are a few data challenges. For example, the data we have has mostly are unlabeled. Only a very small portion of them are labeled, meaning a lot of part of the protected area has not been frequently patrolled by the patrollers before. And besides, the labels that we get, which indicates whether or not there is poaching activity, has uncertainty, especially in the negative ones, meaning if the data tells you that there's no poaching activity in this data point, in this region, it only means that the patrollers didn't find poaching activity in that region in the past. It doesn't mean that there is no poaching. And the third challenge is that there's a huge data imbalance. The positive data points is way less than the negative data points. So we came up with a series of machine learning methods, including combining unsupervised learning and supervised learning using Gaussian mixture models, decision tree ensembles, Markov random fields all together to make this prediction. And we were able to indeed get some promising results based on like the AUC testing and those standard metrics. But that's not what we actually want to achieve. We want to see whether the predictions are indeed useful for the stakeholders. So we send the rangers to 2 areas that are predicted hotspots but are not frequently patrolled before. And during these tests, the patrollers found many signs of human activities and successfully removed 1 row of elephant snares before they were deployed. And that means with our prediction, the rangers patrolled a place that wouldn't have been patrolled, and we found areas where elephants could have been patrolled. And if you compare the numbers of the hit rate, meaning the number of times that we find snares in a month, in this single month of field test, it outperforms 91% of the historical months. So following the success of this 1 month field test, we conducted an 8 month field test. During that period, the rangers are sent to 27 chosen areas and patrolled for more than 450 kilometers. And our learned model predict these areas to be high threat or low threat areas. And we found that the catch per unit effort, which is the number of snares being found per kilometer walking, is 10 times higher in the high threat group than that in the low threat group. This means our model can indeed differentiate the high threat areas from the low threat areas. And after these successful deployment tests in Uganda, we kept improving the learning framework and brought the research to new sites. In northeastern China, we collaborated with the Worldwide Fund for Nature and Huangnihe Forest Bureau. And many of these geospatial features that are needed to make the prediction are not readily available in this area. So we tried to also extract these features from satellite imagery. And this would also significantly reduce the workload of our collaborating site managers. Besides, to deal with the data imbalance and the lack of labeled data problem, we try to exploit human experts' knowledge by asking them to provide like an estimate of threat level for each small regions, and then use that to augment the data set based on those estimates. We also improved the machine learning model by using an ensemble method that combines various base models, including neural networks. And with this, we were able to run a 2-day field test in 2017, where we found 22 snares in these 2 days. And luckily, in this two-day field test, I went back to China and went to patrol together with my collaborators. And here's me removing the snare from the tree. And even my collaborators were very surprised by this result because they didn't expect this area to have snares at all before the test. And during the second day of test, they were even joking that, oh, Dr. Fang, your algorithm is not working because we haven't found any snares so far. And then after 20 minutes, we found an area that has a lot of snares. Yes. Is there any question? Or okay, so yeah, so to are we running out of time? Just to make sure. We probably still have a few minutes. So yeah, we continue to run more tests in this area, and we're looking forward to the upcoming test in 2012. And since we now can make predictions of the poaching hotspots, but we still want to design the patrol routes while taking into account how the poachers would react to the patrol strategy. So we continued trying to say, oh, let's use the machine learning model, the learned machine learning model as a black box and try to do the patrol planning task. And here we treat the learned model as a black box that takes as input the current patrol effort vector and outputs the probability of finding snares. And we want to determine the patrol effort vectors such that we can maximize the sum of these yi's, subjected to scheduling constraint that the patrollers always starts from a certain patrol post and come back to the patrol post after, say, 6 hours of patrolling. And with this, we can solve this optimization problem through building a mixed integer linear program. And it all sounds promising, but when we try to present these suggested patrol strategies to the site managers of a conservation site in Malaysia, they told us that this kind of routes are not feasible in practice. Because to understand why that's not feasible, so we went to Malaysia and conducted trial patrols in the jungle. And this firsthand experience tells us that the terrain here is so complex that we just cannot simply tell the patrollers to move from one grid cell to a neighboring grid cell. So we designed the patrol planning algorithm by first building a virtual street map for the area based on the terrain information, and then compute the optimal patrol strategy. So the resulting strategy now is a probability distribution over the patrol routes that are compatible with the terrain. And this led to the field test in Malaysia, where multiple animal signs and human activity signs are found, indicating that we have led the patrollers to the right direction. Now, this whole project with the nice name PAWS is successfully integrated into SMART, which is a spatial monitoring and reporting tool that is being supported by multiple global conservation agencies and used by more than 600 conservation sites worldwide. So we're hoping that by this integration, these site managers can easily make use of it. And in fact, some parts are already using it to predict poaching right now, and there are more field tests on the way. And we're excited about these successful field tests and deployment of PAWS. And these tests, in turn, reveal a series of new research challenges. And in the past few years, we have been developing new AI techniques to tackle those challenges. I'm only listing 2 examples here. One is how to design patrol routes that are adaptive to real-time information, such as footprints found by the rangers. We developed a Markov game formulation and designed a multi-agent reinforcement learning algorithm to solve this game. Another challenge is in some conservation areas, the conservation drones or UAVs can be used for nighttime patrol. And how can we coordinate UAVs and human patrollers? We designed deep learning-based detection tool and tested in the field. This is the field test, and further developed a game theoretic model for the coordinated patrol problem, while taking into account that the UAVs not only can detect the poachers, but can also use flashlight to deter poachers. Just like what we use for Bayesian persuasion, we can use the signal to try to maximize the effect of our patrols. So yeah, like this flashlight here. So that's what we have done for the wildlife conservation. But we noticed that in many other societal challenges, the interaction between these decision makers going beyond the defender-attacker type of model, which requires new models and new techniques. For example, in recent years, food rescue platforms start to play a role to reduce food waste and improve food security. In Pittsburgh, we have a platform called 412 Food Rescue, and it rescues good food by connecting the restaurants, grocery stores, and cafes that have perfectly good but not saleable food with local communities in need of food, for example, single mom shelters. And this platform relies on volunteers to deliver the food. it posts food rescue requests on the smartphone app, and the volunteer can claim a rescue on the app and help deliver the food, pick up the food from the donor and deliver it to the recipient organization. And some of these photos are actually taken when I myself worked as a volunteer for the platform and delivered food from our CMU cafe to a local community. And in this problem, it's not a defender-attacker game. And we try to see how AI can help. So after talking to the CEOs of the platform, we learned that one pain point is that they are uncertain whether or not a rescue will be claimed by the volunteer. Because if it is not claimed, the food would go waste. So we focus on the interaction between the volunteers and the platform and try to figure out how AI can improve these the notification and intervention scheme. That is how they try to send notifications to like call for volunteers. What they used to do is that after the rescue request is published, they will send notification to all the volunteers within 5 miles of the pickup location and wait for 15 minutes. If no one picks up the rescue at that point, they will notify all the volunteers on the platform. And if 16 minutes before the deadline, the rescue is still not picked up or claimed by any volunteer, then they will have human dispatcher jump in and try to talk to some of the volunteers that they are familiar with and like just try to send a personal note asking them to help. But of course, they don't have a lot of human dispatchers, and also they don't want to send too many notifications to the volunteers to get them bored. So what we want to do is that we want to change or modify their current notification scheme slightly by just changing these parameters to reduce the human dispatcher's workload and to reduce the notifications sent to the volunteers if possible. And we formulate this problem as an optimization problem that can minimize the number of notifications plus the number of human interventions needed, subject to the constraint that the expected rescue claim rate is at least the same as the current practice. And here the parameter lambda is just controlling the impact of these two factors. And we use historical data to estimate the expected numbers and solve this optimization problem through branch and bound. And by varying these values, we get the values of lambda, we get a Pareto frontier, and we found two promising schemes that can potentially improve over the current practice. And we show that if we send the first wave notification to volunteers within 5.5 miles of the pickup location and wait for 16.5 minutes to send the second wave and ask the human dispatcher to intervene 45 minutes before the pickup deadline, we can hopefully reduce human interventions without increasing the volunteer notifications. So this new scheme has been deployed by the 412 Food Rescue since February 2020. We collected and analyzed the data before and after the deployment of this new scheme. And as we all know, the COVID impacted people all around the world starting from early 2020. And in Pittsburgh, the life here is impacted significantly by COVID since the beginning of March. So we separated the data before March and after that, and we observed that after the new scheme is deployed, the claim rate goes up, the average time needed to have the volunteer claim it goes down, and the average number of notifications sent is lower. And this trend continues even after the COVID impacted the area. And these preliminary results are promising, but I also want to make a note here that we know that there might be many confounding factors. And to get a more confirmative claim of the impact, controlled experiments will be needed. And in fact, at the same time, we also proposed an even newer notification scheme that is based on the recommender system to further improve the notification efficiency. We try to use the features of the volunteer and the features of the rescue to predict how likely this volunteer will claim this rescue and use that to design the notification scheme directly, instead of just using the distance to determine who to send the notification to. And we are running new field tests. We are working with our 412 Food Rescue, so hopefully the test will start in weeks. And we also checked with the more like theoretical aspect of it. Like we're doing this learning from data and then optimize the scheme and deploy the notification scheme and then collect more data and learn from it. But is this the best way? Like, what is the best way to do this iterative process? how we know that there's no enough data to begin with, and we also know that the intervention that we use might affect the data distribution, and we may not know perfectly the objective function to optimize for. And we proposed the so-called bandit data-driven optimization and designed a no-regret algorithm to solve this optimization problem. So for this part, it is a little bit far away from the deployment because we are still running the first deployment for the recommended system-based intervention. But we hope that we can have more analysis on the long-term iterative process of designing interventions. So yeah, to summarize, we have been working on leveraging AI to tackle different societal challenges and coming up with game theory and machine learning methods and trying to deliver benefits to the society. So I'm happy to answer questions with that.